Good night, everybody, to this presentation called What Exactly is a Resource Allocation Competition, RAC, Compute Award. And I just want to highlight again here, this is specifically about what a compute award is, differentiating it in terms of its form in the way that it's implemented compared to things like storage allocations. My name is James Desjardins. I'm one of the analysts with SharkNet. I also sit on a couple of national teams that deal heavily with the implementation and the tracking of resource allocation competition awards. So I sit on the scheduler national team that's responsible for implementing the way that compute allocations are executed on the cluster, designing the share system of the scheduling environment to distribute as fairly as possible compute resources. I also sit on the data analytics national team, which is heavily involved in a lot of the reporting that we do, including reporting to the technical teams that do technical reviews of resource allocation competition proposals. And what I like to do whenever we have general interest webinars is I like to take these opportunities to gather some thoughts that I have from tickets that I handle throughout the year. And in particular, I like to handle a lot of the tickets that have to do with wait times and specifically wait times associated with resource allocations. And this presentation is basically a sort of a coming together of the conversation that I would like to have with researchers whenever these wait time issues come up or concerns about making deadlines and how to make the most out of an allocation or report on the consumption of allocations in the past. And it can be kind of confusing with a compute award because it's not a straightforward quota. It's basically a share of the system that requires consumption. So this is basically the conversation that I would like to have with researchers that have allocations or are thinking about having allocations. It is also a good opportunity to understand how much consumption you can achieve without an allocation through the rapid access services. So let me just move forward here. So in terms of an overview, these are the topics that I'm going to cover. So just first of all, what is the resource allocation competition, the RAC? What is the relationship between capacity, allocations, and the utilization? Next, we have to talk about the Q state of the compute capacity saturation. This is to say that the resources that we're making available are in extremely high demand, and the sharing of those resources is a very important part of what we're doing, which is really the origin of the resource allocation competition. The difference between allocating storage and compute. These are two things that are very different. And whenever we're trying to understand getting a compute award, if you're thinking about it in terms of getting a storage award, some confusing things can happen because compute isn't like a bank account. It's not something that you can fill. It's something that sort of has to be consumed over time. We'll also emphasize the difference between the rapid access services and the resource allocation competition allocated resources. At the end of the day, they're actually exactly the same in terms of they're really just quotas and target shares of the system, whereas allocations have a fixed size over the allocation period. Um, and basically don't vary, and they can be much larger than the rapid access services tend to be. So in order to understand how this all works, we also need to understand how to calculate usage of compute resources, because it's how the usage is being calculated that's compared to the target share of resources, which is the form of an allocation. So what we end up doing at the end of the day is comparing compute usage to the target share of an account. And we'll basically look at examples of how this works and how there can be different states of an account that result in either expected or unexpected wait times. And then we'll talk more generally about the global sort of capacity of a system and what we're doing, and how the dynamic state of compute target shares and usage. So this is a very dynamic state, which is why a target share allocation can be a pretty confusing thing to monitor on these clusters. And then finally, we'll go into visualizing the job resource utilization time series on a portal that the analytics team is developing at portal.alliancecan.ca. We'll go over a few views of that um, to sort of help if at any time you're concerned about a wait time, you can go to this portal and examine the usage history to be able to determine if a wait time is expected or not expected. And if you determine that this wait time is not expected, it shouldn't be happening, that's basically the great time to submit a ticket. And I will probably end up taking a look at the case in there. And then finally, I'll just go over some past presentations that go into more details about specific aspects of what we end up talking about today. Okay, so the first thing, what is the Resource Allocation Competition, or RAC as we call it? So if you were to Google Alliance and Resource Allocation Competition, you'll go to the Alliance webpage here, and then it will say down at the bottom, basically it's access to compute, storage, and cloud resources beyond what can be obtained via the Rapid Access Service, or RAS. RAS is basically what you have available to you as soon as you get an account. No need to apply for anything. It's just there. And then whenever you do that, the first link basically sends you to our wiki page up here. And then you have the key dates table, and you'll see that the current end to this allocation open session is November 4th. And you'll get all the other information down there, including links that go down into even documentation about some of the analysis tools that I'll be talking about in this presentation. So we're going to start off. This figure is actually the punchline of the whole presentation. At the end, this describes sort of the state that happens whenever we're looking at computation on the system. But just for now, we want to understand that the resource allocation competition and the awards that are given really sort of define the relationship between a compute capacity, the allocations, and then the utilization of the system. So in this case, the capacity is the total installed hardware for the resources offered by the Alliance. So in this case, I'm just going to, this inner circle here is a representation of 100% of, let's say, the GPU resources on a compute cluster. Okay. In this case, I've just sort of drawn it out, and we'll see what these numbers are about later. But we say, let's say 60% is basically assigned to resource allocation, while 40% is assigned to rapid access. But we'll get into that later. The second part are the allocations, and the allocations are the quotas and target shares controlling the consumption of the resources from the groups. So this is the total capacity of the circle. And then here we basically have one allocation, which is a portion of those resources. We have another allocation here, which is another portion of those systems. And then the remainder of the resources is broken up into equal parts. And these are basically default accounts, or the rapid access services. Now, the utilization is the consumption of the resources by the groups. So in this case, that's the outer ring, where we can see that this RRG1 group is actually consuming at this given time more than their target share. This RRG2 group is consuming less than their target share that's over here. And then we even have default shares down here that are consuming more than their default target share. So the main thing I just want to get across here is this is all based on there being an installed capacity of resources on the system. Those are separated into allocations, or in terms of compute, those are target shares. And then those target shares dictate how the actual consumption of all those resources occur over time in a very dynamic way. And that really defines what it is that you're applying for when you apply for a resource allocation competition compute award, which is one of these things or one of these things, which we'll get into the details of moving forward. Okay, so what's really important to understand at the same time is we have resources that have a capacity. There's a a determined number of GPUs installed in a compute cluster. So we then have scheduling software that will distribute jobs that are requesting certain quantities of those resources onto those compute nodes over time. So the cluster compute capacities are in constant high demand. So the quantity of resources requested in queued jobs at any given time is typically multiple times the size of the installed capacity. What we have down here in this figure is a representation of all of the resources that are allocated to jobs over the period of the last couple months. So I believe this is on the new NIBI cluster, and this is a quantity of GPUs. So every day, this is the count of GPU days that were allocated to running jobs down here, those colored bars. So we basically have not too far over 200 A100 GPUs installed there. And that's how many were allocated over time. These gray bars represent the number of those GPUs that belong to jobs that are waiting in the queue. So this is what I mean by typically the queued resources are multiple times the size of the system itself. So for example, um, whatever day this is, the beginning of September, there was more than 10 times the size of the system of A100 GPUs being requested to jobs that were sitting in the queue. So the load is very heavy, and the scheduling software's role is to get as much of that work deployed to compute resources in as fair of a way as possible. So that's another aspect of where the resource allocation comes into play. So what's the difference between allocating storage versus computation? So let's say over here, we're talking about the total storage that's allocated on the system. What we can do is we can create storage quotas. So a quota is basically a limit that we put on the storage quantity of an account. So in terms of storage, we can say the allocation is a quota of storage. If this group starts consuming that storage and gets to the end, then the quota creates a limit. No more storage can happen on that file system because that quota has been consumed, and then nothing can go beyond there. But typically, what will happen over the time is that storage will remain for an account. And this is an important part in terms of storage because you need the space there to be able to fill up as your data comes in, as you're collecting things. So for storage, there needs to be these basically empty spaces that the projects can fill and accumulate. So basically here I've shown that this here is RRG1. It's called an allocation that has 40% of the storage on the system, and they've used the entire thing. This second allocation here has 20%, but they're only using 5%, and the rest of it stays idle because that's a quota design. Now, for computation, the difference is that what you're getting isn't a quota. It's not that you basically have access to a compute node and you're either using it or not. What you have is a target share of the system. And the important part here is that unlike storage, which it's important that there is empty space for allocations to fill, we never want any of the usage of computation to ever be idle. We always want it packed, running as much computation at any time as possible. Now, we also know that it's the case that researchers aren't running a fixed amount of processing all the time. Researchers tend not to submit, their allocation every day and have it run the same every day. You want to get a lot done for a deadline, then you're idle for a while, you collect some new data, you have a big batch. So the time series of usage fluctuates a lot, but regardless of all that, we're trying to maintain a constant state of this usage circle always being complete, where there are no idle resources not being used. So the way we do that is with the target share, and that's the main thing that we want to talk about today. So what's the difference between the rapid access service and a resource allocation competition allocated resource? So they're actually the same thing. Both RAS and RAC take the form of quotas when it comes to storage and target shares when it comes to compute. They're really expressed the exact same way in terms of implementation. Now, the rapid access services are limited in size, and they're limited in size in a fixed way for storage, where we say you can, on different file systems, this is the maximum that you can request in the rapid access service. In the compute side of things, we're going to get into the details about what the limiting factors of the size of the target share are. And that's a very dynamic thing on these compute clusters as we try and maintain that the compute of the resources is always as saturated as possible. The important thing that you'll see is that a RAC allocations, well, they have an application process, where the rapid access, there's no application process. Once you have an account, you have access to those compute resources. The RAC compute allocations are of a fixed size. So this is the thing that we're going to get to for the allocation period. So what we're going to get into next is how the shares of the system actually get consumed and how that actually impacts the size of default or RAS target shares compared to what a resource allocation can expect. And what they can expect is basically a fixed target share at the awarded size of the compute resource that they got. So in order to get this, let's just go through a quick review. I've given this description of calculating usage of compute resources in previous presentations I'll talk about a bit in the past. But basically, job shape and the measurement of resource consumption is done in a way that you can visualize a job as a multiple dimensional rectangle. And in this case, we're talking about time and billing units. So each of these rectangles is a representation of a job. where time is on the X, and then the billing unit, which is something like CPU equivalent or RGU equivalent, is on the Y-axis. So these are 3 jobs here. This one basically was submitted and started right away, and the green area is when it was running. This one was submitted. It waited a little while. You can see that gray area, and then it ran for this period, and it ran in less time than the time limit requested. So there's this extra little square at the back. And then similarly, this job was submitted. It waited a little while. It ran for a little while, and it ran for less time than it requested, which is this big thing. Okay, so that's a representation of basically all of the jobs that came out of an account. And these are just stacked on top of each other. And then they're basically their submit times, their run times, their end times are all there. So from this representation, the height of this is the billing unit, which is basically a representation of the amount of resources that are being made unavailable to other researchers while those resources are allocated to this job, which is typically for CPU jobs, a combination of the CPU and the memory, and for GPU jobs, the performance of the GPU, which is RGU, plus the memory, plus the number of cores. So by summing the billing units at each time point across all the jobs provides a time series of resource consumption. So if we take all of these green areas in the figure above and sum them, we get this representation of the quantity of resources consumed over time. A similar time series can be generated for pending resources. So if we sum all of the pending resources at any time, the ones that are waiting in the queue, we get this gray line that's in here, where we see there are periods when there are resources pending, but nothing running. Then these metrics can be compared to the account's target share to determine states like expected wait times. So this is the representation of resources that are allocated to running jobs, which we'll refer to as utilization. This gray line is the representation of resources pending or waiting in the queue. And then this gray area is a representation of the target share for the account that was running these jobs over time. So based on the relationship of this usage over time and the account's target share over time, we can determine things like expected or unexpected wait times. But this relationship is entirely what a RAC compute allocation is. A RAC compute allocation is this line, which over time is compared to the consumption of resources to then determine the priority of jobs that are submitted from that account. If over a period of time, the computations achieved are greater than the allocation, then priority goes down. If over a period of time, the computation achieved is less than the target share of resources over time, the priority goes up. So in this case, a period of time where there is relatively little utilization resulted in this account's ability to have more utilization than their target share, which we refer to as bursting. But at other times, when the utilization has been larger in the past, you can submit jobs, the priority would be low, and then those jobs are less likely to allow you to accumulate utilization again. So this area of bursting can result in a period of time that we refer to as expected wait times. So Comparing compute usage to the target share of an account. So if we convert the resource consumption time series to a cumulative sum, this provides a view of how usage is relating to the target share over time. So this is the figure that we were looking at before, where we saw it translate from job records into a time series of usage. But if we convert this into a cumulative sum and the target share into a cumulative sum, we have the figure up here where the target share cumulative sum goes like this, and the usage cumulative sum goes like this. And then we can see clearly why um, there, there are wait times. If the entire system is running the way that it should be, allocation accounts should be able to do exactly what we see here. That if they're not active for a while, they can submit work and then they can catch up to their target share. And they can go above their target share and they can keep working. But then once they're above their target share for a while, the system will implement wait times that basically cause plateaus in the usage and then allow the other allocations or the other default accounts to catch up with their resources over time. Okay, so now let's talk about the sort of global dynamic state of how all the shares on a system are working. So the dynamic state of compute target shares, and this also describes usage. So in the next page, we'll get to that final diagram. That's the punchline of this presentation. So the sum of target shares is equal to the compute resource capacity. So initially we talked about this inner circle being the capacity, the number of resources. So for example, the number of GPUs on a system. Then we have allocations. Those are the target shares, which are given to RAC accounts. So in this case, we're calling it RRG, or Resources for Research Groups number 1. This is a target share for a second allocation, RRG2, which is smaller. And then we also added an RRG3 and an RRG4. Okay, so this is part of what we do in the allocation process. We determine the system capacity that we are going to allocate to the resource allocation competition. Traditionally, it's been 80%, and then 20% of the capacity is left for the rapid access services, and those are the default accounts. So of the remaining shares, it gets divided equally across all default accounts that have any job pending or running on the system. That's a calculation that happens, I believe, every 7 minutes around there on the system. It calculates that the target share of a default account is the RAS proportion of shares divided by the number of active default accounts on the cluster. Okay, that's great. Now, what ends up happening is that some accounts do not have jobs queued or running at times, making their target share idle. So in this case, this representation says that RRG1 currently has jobs running or queued, although I'm not displaying it in the outer ring. And let's say RRG2 also has stuff that would be in the outer usage ring we talked about before. But these other allocation accounts don't have any jobs in the queue or running. So what we do with this space is referred to as slept rack. This is basically saying that the resources allocated to those accounts is not being consumed. So we're going to sleep those shares of the system. So idle rack allocations enter a state that we refer to as slept rack, and we'll see what that ends up producing on the next slide. So the slept RAC shares are passed to the rapid access service pool to be equally divided among the active default RAS accounts. So this is now the same number of default accounts that we saw in the previous figure, but they now have access to 40% of the system because 20% of the shares that were allocated were being left idle for all kinds of good reasons. And my cat wants to get up on the table. We'll see how that goes. That's fine. Okay, so what happened here is that from the previous slide, if I go back, the RAS shares increased in size, but the number of default accounts that were active, which is 10, that number stayed the same. But basically, the size of these target shares increased, basically doubled in size. But the size of these default shares also changes based on the number of default accounts that are active. So if it's Monday morning at 10 a.m., a bunch of default users submit jobs, the quantity increases from 10 defaults to 20, and then that makes each of these target shares half the size of what they are here. But importantly, that's the state of the rapid access shares. It's trying to make the share of resources as big as possible, making sure that rapid access is a substantial resource that many researchers can get access to, and we try and minimize the requirement for the RAC allocation. But the RAC allocations, when they're active, never change size. So the important thing here is that the RAC allocations in terms of target shares on the system are actually exactly the same thing as a rapid access service default share on the system, except for RAC, they're larger than what you can expect typically from a default account, and they never change size during the allocation period. No matter what else is going on anywhere on this system in terms of the amount of load, the number of accounts, how much different accounts are asking for, the target share of an allocation is fixed for the period of the allocation. Now, so the RAS compute target shares vary in size based on the size of the slept RAC shares and the number of active RAS accounts. But importantly, both RAC and RAS usage is able to burst beyond their target shares. And this is a very important aspect of all of this. So here we have, again, the total capacity that's divided into a portion that is determining basically the size and the quantity of allocations that we're able to award. We have an allocation size here for this group, RRG1, that has this big allocation. And then it's actually utilizing at a given time all of its allocation, plus it's bursting beyond the allocation. So this total usage is larger than the allocation at given time points. And this is all determined whether or not the account is above or below its target share trajectory over time. So in fact, this allocation account, RRG2, is currently utilizing less of its target share. Now, the important thing with this account using less than its target share is that's either because they don't need much of it at this time and they don't have their target's worth of resources submitted to the queue, or in the past, they had bursted beyond their allocation, and now the scheduler is restricting them down to just a portion of their target share to allow these other accounts that were below their target share to catch up. So that's the goal. The whole time we want the usage ring to represent basically that as close to 100% of all of the resources are actually in the state of being allocated to running jobs. And over time, as the allocations and default users come active and inactive, that over time, the allocation accounts are able to achieve that target share over the period of the allocation. So given all that, what we've done is we've made a portal, the portal.alliancecan.ca, that provides researchers to view their accounts usage over time with different fields on it. So this is a representation of a group. I don't have the group name on here. You can select the system that you're viewing. You can select the time period that you're looking at, and then you can select the metric that you're displaying. So for CPU jobs, the CPU equivalent is typically the billing unit. And then you can also change the summation. So for total, we're just looking at the total CPU equivalent days every day. We've also enabled the target share to be displayed here. So we can see that this account was not running anything, was running less than its target share, and then was running more than its target share. And then if we go to the next page, we can also show the queued resources. So these are the number of GPU or CPU equivalent resources that were waiting in the queue. So likely in the past, there had been a bunch of high usage, and although there's resources queued, they weren't running. And then we can see those resources get consumed over this time. Then more resources are submitted, and they get consumed over time like this. And then that balance, so that the resources can stay at the target share over time, is achieved. So if we look at the cumulative sum of this one, it doesn't look like the usage is keeping up with the target share over time. Although right here, they are actually catching up uh, to the target share, but they never really meet it, and then they basically don't have things submitted there. So this is a representation of the account we were looking at before, and basically the view that you can just access on this portal. So we see that over time, the target share looks like this. And then the research group didn't have much going on. And then their usage was below the cumulative sum, and the scheduler allowed them to catch up and surpass it by quite a bit. So at this time, the account had bursted above their allocation and then plateaued for a while. We don't know if this plateau is because the account wasn't submitting anything or if the scheduler was throttling the usage. But then it's basically brought back down to the target share, and then there's another plateau over here. So if we look at that one in terms of the instantaneous usage, we do see, even though the queued resources are being displayed, this account was basically able to run everything it wanted without wait times, although we can see there are a couple wait times here. And then it got, over this period, it got well above bursting over its target share, and then the scheduler imposed a wait time for those resources, which, would have happened right around here in this plateau. So although they had resources pending, the scheduler was trying to bring their utilization back to the cumulative target share. So, and then another thing that varies in this, looking at the cumulative sum of the target share versus the cumulative sum of the usage is really the best way to understand where an account is relative to consuming its target share that was awarded. But another variable over time is a decay or a half-life decay. And that half-life decay is basically how much the scheduler environment forgets past usage. So this green line, I believe, is called, it's Slurm's raw usage line that we pull regularly. This green line is a representation of the cumulative sum of the usage plus a decay. So it's basically how much the scheduler is forgetting past usage. This allows, and these values of raw usage are what the scheduler compares to the target share in order to calculate the priority of subsequent jobs submitted by this account. So that's also available just by selecting the raw usage when you're at the portal. So in this case, you can see it very clearly that they burst over their usage. The raw usage goes up. It goes through the process of forgetting about it. And then the account submits a whole bunch of other jobs. Now, although you can see that the usage is at a constant rate, the cumulative sum is asymptoting. And then once the usage ends, the decay rate is visible there. Over this period of time, the usage is actually above the target share. We still see an asymptote higher, and then the decay over time. We'll also note in this case that the target share is not fixed, it's varying. So this is a default account where we can see that basically this is probably averaging around 250 to 300 core equivalents, which was a typical default target share on the previous generation national general purpose clusters. So we're almost at time. I just want to go over a couple of previous presentations on this topic. So we've been doing these presentations for quite a while. And because I'm coming from the scheduler team and the analytics team, I tend to focus on being able to interpret past usage. So a previous presentation that sort of expands on interpreting the views of past usage that are available through different portals is available on our YouTube channel. It's called Exploring Compute Usage from User-Facing Portals on National Clusters. This presentation sort of describes in more details the computation of past usage, goes into more details about the portal I talked about, but also looks at the site portals that are available for NIBI and Rorqual and Narval, and it gets into the actual performance of the computations inside of jobs. So although I was talking today about utilization being the amount of resources that are allocated as jobs, the actual performance within a job is very important, and these portals allow you to look into that. There's also just a quick video is once you get to the point where you realize it's very important that the resources that you're requesting and the resources that you're allocating to running jobs should match the actual resources that the process requires, although it can be difficult to determine or to sort of estimate what those resources are. There's a quick little video on estimating the memory usage of a process with an interactive job allocation and using top. I think that's just like a 2-minute type video. And then previously there was exploring properties or job properties with the ViewClus Python package. So this is a Python package that we developed a while back. I believe this one actually, you can create a notebook and then you can pull your job records using sact, the scheduler command, and then use this notebook to generate a bunch of the figures that I typically use whenever I'm debugging a wait time investigation. And then you can do all kinds of custom explorations with that, trying to determine if certain wait times are relating to different job properties or not. And then with that, I believe that's it for this presentation, and we can open it up for discussion or questions.